If you remember, in our first lectures, at the beginning, we considered only one atom. And we were able to define the electron structure of this atom. So then we considered two atoms, trying to guess, based on the electron structure of each atom, the type of atomic bonding which we can expect when we are fabricating material from these elements. However, in general, you know that material involves not two atoms, but millions, billions of them. And it appeared that these millions of atoms, they arranged in some very special structures, so-called crystal structures. So in this lecture, I will introduce some very basics of the crystal structure level of materials, and then we will consider several examples how this level of structure, which is on the order now of 10 and more angstroms, define the material properties. So, indeed, so materials packed, if you want, in some very special structures, so-called crystalline structures. And so it means that atoms pack in periodic 3D arrays, all of them, metals, ceramics, some polymers also. This packing can be indeed very nicely organized to have very nice periodic structures. However, also you know that in some cases, same millions of atoms can be not arranged in these nicely arranged structures, and they don't have the periodic packing on the large distance. And in this case, we are talking about the non-crystalline materials, amorphous materials. One of the best examples, which for sure you know, so are glasses. So, and this screen just demonstrates you that same kind of material, let's say silicon oxide, can be arranged in the long periodic arrays, 3D arrays. In this case, we are talking about the crystalline structure, or silicon oxide glasses can be not arranged in this specific periodic packing. They may have some very complex structures, and in this case, we may talk about glasses or amorphous materials. Of course, all these two terms, crystalline and amorphous, currently sounds very qualitative for you, and one of the goals of this lecture, of this part of the course, is just to give you a little bit more deeper insight about the difference between the different crystalline structures, as well as difference between the crystalline and amorphous structures. So this screen gives you some example of glass materials, not crystalline materials, which include glasses. And you know that they have very specific properties, including same very high temperature, but on the other hand, you can easily fabricate materials with complex form from them. On the right side, you also can see the ceramics, but crystalline ceramics, which can withstand extremely harsh conditions. On the right side, you can see silicon nitride ceramics, which one part of which you put inside the liquid nitrogen, and you applied fire, if you want, to the other part of your article here. And this article can withstand this condition without failure. It means that this ceramics has extremely low coefficient of thermal expansion, as we discussed before. So again, ceramics, for example, can be crystalline, ceramics can be non-crystalline, and that's what we will talk about. So now let's start with crystals. So how to describe crystals? How many different types of crystals do we have? In order to describe this, let's say try to give a definition to a crystal. What does it mean? So in general, in the simplest case, we may say that a crystal is a solid material, that's for sure. However, we have some exemptions, so we can talk about liquid crystals in principle. But typically it's solid material in which components, atoms, are arranged in very definite patterns, and whose surface regularity reflects the internal symmetry of this packing. So what are the most important terms in this definition? So first of all, definite patterns. It means that I will try to show that the number of this pattern is not infinite, and they defined actually by the indeed internal symmetry of these crystals. All right, so we are talking about crystals, and so these crystals you can see on this slide. It's somehow are characterized by different parameters such as packing. So you have the crystal faces here. So in order to introduce some science inside, these materials, we have to decide to define such parameters, such term, if you want, as a unit cell. This screen gives you some idea what does it mean, unit cell. Unit cell, first of all, is the smallest unit of volume that permits identical cells to be stacked together to fill all space. Again, put your attention to the main terms in this definition. First of all, we are talking about the smallest unit cells, smallest unit. In the second, all of them should be identical. That's, in this case, we are talking about very specific unit cell which correspond to this type of material. And what is also important, they should be able to fill all space in some sense without voids. And by repeating this type of patterns, by repeating many millions of these unit cells, one over and over in different directions in 3D space, one can actually build the entire crystal lattice, and so one can build the volume of any materials. So the unit cell can be represented in different way in order to have some idea. So it can be represented as the hot spheres, and on the right side of the screen you can see this type of representation. And the unit cell is also somehow outlined on this figure, or it can be represented the lattice points. See on the left side you see some kind of cube with some atoms, the blue are atoms, so somehow distributed in this unit cell. The question is, how many types of lattice do we have? So how many different lattice with different densities we can obtain? Are they infinite numbers or it's finite, and so on and so forth? Let's talk about this. So the goal of this type of lecture just to find out that the shape and size of unit cell can be described by so-called point symmetry, and the location of the lattice, or if you want, atomic density of each unit cell can be defined by the translational symmetry. See, symmetry plays a very important role in crystallography, and so when we discuss the point symmetry, we will find out that only a definite number, specifically in our case 6 crystal systems only exist, and this is pretty surprising. And when we'll then discuss the location of lattice point in each let's say specific crystal system, we will talk about the different type of Bravais lattice, and altogether they will define almost every typical crystal cells which we can find in nature. So let's talk about symmetry, and let's talk about let's talk about how many crystal structures, crystal cells, crystal systems we may have. So first of all, don't forget, so by definition, this unit cell need to be able to stack to each other in order to fill all space. Now, this screen in some sense demonstrate this kind of statement. You can easily see that cubes work, so they indeed can fill the 3D volume without any voids. But if we are talking about pentagons, so you know that they don't. So it means that with the help of pentagons in general in the classical crystallography, you cannot fill the space without voids. That's why this type of symmetry, this type of, if you wish, geometry cannot be, should not be considered as a part of the crystal system. So from this standpoint, different types of unit cell are possible, of course, but they was classified based on the level of symmetry. What I'm talking about. First of all, let's see the following way. Instead of talking about the specific geometry or the specific 3D structure, I will just ask you questions. Do you know any kind of geometry which has, let's say, perfect symmetry? It means that has infinite type of symmetrical operations which can be applied to this object. So they will remain the same. And if you think you will provide me the right answer, every time students provided me the right answer, they say, of course, professor, we know it's a sphere. And what is important here? Here it's important that I can define by the set of symmetrical operation any kind of shape of object which exists in 3D volume. So I don't need even to give you a picture or give you a term. I just have only to present you the set of symmetrical operation which you can do with this kind of 3D object, and you will guess what type of object I'm talking about. And that is very, very important. So indeed, in the case of spheres, so we have infinite plane of symmetry which passes through the center, and infinite rotational axes also are present. And no matter how little or much we rotate, let's say, this sphere along this axis, it will remain the same, appears the same. So it means that this kind of 3D object can be described by this number of symmetrical operations. So now let's go, spend a couple of slides to a deep, let's say, fundamental part of science, which has named space group. Idea is very, let's say, simple, based on our previous discussion, that indeed, any motifs, any kind of, if you want, cells or periodic arrangement can be described by the sets of symmetrical operation. That, let's consider again example which is shown on this screen. So let us apply, for example, the rotation of 90 degrees about the center of the pattern, which is shown on this screen, and you will find out that the pattern which will repeat itself 4 times during the rotation on 360 degrees. On the other hand, so we are talking about so-called point or rotational symmetry for this type of object. On the other hand, we can apply a linear shift or translation of the pattern by a certain amount. For example, for the length of the small square of this object. And again, you will see that this object will repeat itself. And again, so now we are talking about translational type of symmetry. So 2 types of symmetry exist, rotational point and translational symmetry. So the field of science which describe this kind of very interesting transformation is called the space group. And space group of crystals, they defined the symmetrical operation which can be applied for these crystals. And analysis of this operation showed, and I will show you a little bit more about that, that only very finite number of 3D objects, if you want, can be considered at the unit cells. So let's talk a little bit about translational symmetry. On this screen, you can see the TEM image, actually, the image of crystal on the atomic level. And so you can see, as in previous slide, so we can see easily here the translational symmetry for this crystal structure, which just the real crystal structure obtained by the transmission electron microscope. But you will see that translational symmetry is not macroscopic. So the translational symmetry takes place on the order of atomic scale, which we have discussed on the previous lecture. That's why on the first step of our analysis of the crystal structure, we will consider only the macroscopic type of symmetry, point symmetry. And translational symmetry will give us, then further analysis will provide us the number of Bravais lattice. So point symmetry, what kind of point symmetries do we know? First of all is just reflection in a point or inversion, and I believe in general you know what I'm talking about, and next slide will demonstrate you what does it mean, and we will talk about center of symmetry in this case. The second type of symmetry is reflection in a plane or mirror symmetry. I believe you also feel what does it mean. Rotation about the imaginary axis or rotational symmetry, for sure also very well known for you. And the last one, not so known, so-called rotation and after inversion or rota inversion. So I will give you example and you will understand what does it mean. So in general it was shown only these 4 types of point symmetries should be considered in order to describe all known classical, let's say, unit cells, crystals. So center of symmetry, that's a screen, demonstrate you what does it mean. The item consists of 2 asymmetric faces, as you can see, and every part of the item can also be found on the opposite side of some point. In this case, it's just center of symmetry at the same distance. So this is reflection in a point or inversion. So mirror symmetry, this screen demonstrates mirror symmetry, and you can see that many letters, for example, they do have mirror symmetry. Moreover, put your attention that some letters have mirror symmetry in 2 directions, some only in 1 direction, horizontal, the other only the vertical mirror planes, doesn't matter. So that's what we are talking when we are talking about mirror symmetry. We have to have in our mind this very simple example. Moreover, people and so they have mirror symmetry in biology, and it's called bilateral symmetry in some sense. So each human being also has mirror symmetry and can be maybe in some case described with the help of this type of symmetry. So rotational symmetry, very straightforward. Only put your attention that that's may have the 2-fold symmetry, 3-fold rotational symmetry, 4 and 6-fold rotational symmetry, which simply means that the figure looks the same n times, 2 times, 3 times, 4 times, 6 times in a 360-degree rotation along existed axis. So this is called n-fold symmetry. So 1-fold symmetry means no symmetry at all. Finally, n-fold rota inversion symmetry means that the object will be first transformed into itself after the following 2-step operation. First of all is rotation of 90 degrees along the some axis, and after that followed by the inversion with respect to a point on this axis. This is n-fold rota inversion symmetry. So again, many objects, they may have different types of symmetry. They may have rotational symmetry, and at the same time they may have the mirror symmetry, and they may have the 2 types of mirror symmetry, and so on and so forth. So again, what is the main idea? It means that each object we can describe with the help of the set of this symmetrical operation, and this is very important for us. So the sets of basic symmetry elements for crystals are shown on this slide. It means that analysis of whatever sequence of these symmetries which we discussed with you, so allowed scientists to conclude that only this type of symmetry which are presented on this slide should be used in order to describe any kind of crystal structures. Only this one and none of them. And just put your attention that typically, and that's you can use in your future, mirror symmetry has symbol M, center of symmetry symbol P, and 4-fold rota inversion. So they have unique symbol for star. Analysis of all these symmetrical operations, specifically rotation, reflection, and rota inversion, and all their combinations showed that somehow we can subdivide all these objects in the total of 32 unique possibilities. So based on that, it was decided that all crystals can be classified in the 32 crystal symmetry classes. 32, it's not infinite, and it's very good, However, 32, it's it's not small number. That's why the next analysis of these crystal symmetry classes allowed to combine them in the 6 so-called crystal systems. And so these crystal systems are the following: the cubic one, the tetragonal one, hexagonal, orthorhombic, monoclinic, and triclinic. So see, the nature appears to be extremely clever. So that's based on the analysis of symmetry, taking into account that all these 3D objects which we are analyzing with the help of these symmetrical sets also should cover the whole space without voids. So nature gives us only a very small, I want to say, number of the crystal systems which may exist in nature. And that's a system we will talk about. So first of all, we have to consider we will use the crystallographic axis. You will see this crystallographic axis A, B, C in order to define these different crystal systems. And using this axis, it's easy to define them. And let's start with the cubic or isometric system. So in this case, it's very easy to say that all objects which do have the crystallographic axis equals to each other and they intersect under the right angles, they belong to the cubic system. So the easiest one, and not is one of the easiest, but indeed the easiest one, is very recognizable. It's the real cube, which we typically use in order to learn crystallography. And the cubic structure in the form of cube exists for many minerals. But don't forget, for cubic system involves 6 different classes of symmetries. Remember, we talked about 32 classes, 6 of them belong to the cubic or isometric system, and 15 different crystal forms also belong to the cubic system. So it's not in general so straightforward. One of them you may see here is the hexahedron, and which also belong to the cubic system. It's one of the 15. And you can see, of course, here, why cubic system has the highest level of degree of symmetry among the other crystals. And because the hexahedron is very close to sphere, which has, as you know now, infinite symmetry in some sense. And that's why it's that's why the cubic crystal structures, the cubic system indeed has the highest level of symmetry as compared to other systems, which we'll discuss just next. The tetragonal system, also very easy to introduce. In this case, 3 axes, they intersect on the right angles, as you can see on this slide. And 2 of these axes are equal to each other, A and B, for example, but one of them is different in length. So a tetragonal prism, as you can see on this screen, is one of the 9 forms in this crystallographic system, and 7 different classes of symmetry belong to the tetragonal system. And this is second crystal system from the standpoint of the symmetry. So of course, if you applied some force and somehow you can make the Cx equals to A and B, so this tetragonal system, tetragonal unit cell, will transform to a cubic one. Next system is hexagonal system, and it's easy to describe this system with the help of the 4 axes. And 3 of them, they equals to each other, and belongs to the same plane, and they intersect in the angle of 120 degree, and the force xc may be longer or shorter than the other 3 axes, and it's the normal to the plane to which belong the axis A1, A2, and A3. So what's interesting to outline that, this is hexagonal system has 2 divisions, if you want. One is hexagonal division, which has 7 classes and 6-fold symmetry. And also there is a trigonal division, which involves the 6 forms and the 5 classes, and has threefold symmetry. In some classification, this trigonal division is outlined as a special so-called rhombohedral crystal system. That's why in one book you can find 6 crystal systems, in the other 7 crystal systems. So then we go to the orthorhombic system, which also is characterized with the help of the 3 axes. In this case, all 3 axes are not equal to each other, while they still intercept under the 90-degree angle. These kind of 3D objects, if you want, and one of them, pinacoid, so is shown on this screen, has 3 symmetry classes and only 2-fold axis of rotation and 1 mirror symmetry. Monoclinic system, again, so in this case, all 3 axes are not equal to each other, and while 2 angles of intersection, so equals to a 90 degree, the one angle between, for example, this alpha and gamma is not equal to 90 degree. Less level of symmetry for this monoclinic system. This system involves 3 classes only and has a 2-fold axis of rotation and mirror symmetry. Example, monoclinic prism is shown on this screen. Finally, triclinic system with and the triclinic pinacoid is shown on this slide, has all 3 axes which are not equal to each other, and all angles of intersection of this axis, they're not equal to 90 degree. Only 2 symmetry classes here, and they do have 0 or 1-fold axis symmetry. So let's conclude, and that's in general, you know, we are just refresh your mind. So we outlined 6 classes of symmetry, and cubic class or isometric system, it has the highest level of symmetry, while the last triclinic system almost 0 symmetry. What is important? Why we are talking about this? So here in this lecture, while this is the topic of a very detailed investigation of the course of crystallography, just in order to understand and in order to remember that these classes, this number of symmetries, they are coming not from the ceiling, and they are coming based on the detailed analysis of different symmetrical operations which can be applied for the different 3D objects, and just having a criteria that these objects should cover completely without voids this 3D space, only very specific number of unit cell can be outlined, which in principle described almost all, I want to say, the crystals which were found in nature. So the next and the last part of this lecture is devoted now to the translational symmetry. So assume now that we do have, let's say, cubic structure. So now the question is, so how atoms can be arranged inside this cubic structure, and or, for example, what atomic density one can reach in different type of crystal lattice. And this is very interesting also questions. And again, so it was found that not infinite number, but very finite number of such kind of Bravais lattice exist in nature. Why Bravais lattice? Because indeed the French scientist Auguste Bravais in 1850, based on the analysis again of different 3D structure, found out that only 14 types of unit cells are compatible with the orderly arrangement of atoms which could be found in crystals. So, and all these 14 Bravais lattice on one hand are shown on this screen. However, we will go now one by one in order you can refresh your mind about what kind of Bravais lattice we are talking about. So again, cubic or isometric cell can exist in 3 different forms. So first of all, we are talking about the simple cubic system or primitive cubic system, and it's shown on this slide on the very left, and letter P is used in order to define this type of cubic structure. The next one is so-called body-center cubic, when we do have one atom which belongs to this unit cell in the middle of the cubic system, while again 8 atoms are sitting at the edge of the cube. And finally, we are talking of so-called face-center cubic, FCC structure, and letter F is used in order to define this Bravais lattice. And in this case, we do have atoms sitting in the middle of each face of the cubic structure. In the theoretical crystal system, we do have two types of Bravais lattice. One is primitive again, as we described before, and the other one is body-centered. So when the additional atom is sitting in the center of the cell. Put your attention that the C-type or base-center structure doesn't exist because it's simply will be a primitive cell with a smaller cross-section of the unit cell. So orthorhombic cell has 4 different Bravais lattice, which include P, I, C, and F, means primitive, then body-centered, then face-centered, and then base-centered structures. Orthorhombic again has 4 different Bravais lattice of P, I, C, and F, as we described before. While monoclinic and triclinic cell, they have the primitive in the case of monoclinic, and C structures in the case of monoclinic system, and only primitive one for the triclinic cell. So very special trigonal cell should be outlined here, which belongs to rhombohedral crystal system, and in this case is unique from the standpoint that so not one but 2 interior points divide the long diagonal of the cell in third, and this is very special and unique Bravais lattice, which belong only to the trigonal cell. And rhombohedral can be thought over the cubic one, but disturbed along the one of its diagonal along which these 2 atoms belong. So as a conclusion, so we describe the crystal systems, and we outline that based on our classification, 6 crystal systems exist, which are shown on this slide. But in each crystal system, we also have the different number of Bravais lattice, which define the crystal system with different density of atoms in this crystal system. And while for a cubic, let's say, crystal system, we do have 3 Bravais lattice. For triclinic, it's only 1, while trigonal, which includes rhombohedral subdivision, has all 4 Bravais type of lattice inside the crystal system. So the next step is to analyze how these crystal structures defined the property of the synthesized material, fabricated material, or considered material. So in the next lecture, we will, on the example of the material density and different mechanical property of this material, we will find out indeed how crystal structure can influence mechanical and physical property of these materials. Thank you very much for your attention.